Good morning. We're going to look at a very interesting topic. I always say it's a very interesting topic because I want that everybody would be motivated and pay attention. You see on the screen there is a circuit in there that we were working to illustrate how to get the transfer functions. Okay, so I am going to take advantage of this example. And what I want to talk to you about is the concept of the root locus plots. Before we do that, I think it's worth seeing the example, seeing the transfer function, and do some basic tests. Where are the roots of the characteristic equation of the system? What can the roots move if we change the values, and how they change? And the second aspect of it is when you change those coefficients, what is the effect on the response of the system? What does it do if you do that? Okay, very good. So we will use this example. I'm going to disappear in here and we'll continue. So here we have that we look for the transfer function where the voltage of the capacitor was the output and this voltage here was the input. So if we apply the Laplace transform to the equations of the system, we obtain this transfer function. But if we solve with the simultaneous algorithm, um, we also found this out this way. Or if we do it with the von Graph model of the system, we found the transfer function here, like that. So what I suggest we do is we look at the transfer function first, the one that we have in here, and we give it some numbers in such a way that we could enter them into MATLAB and see what it does. So I am going to basically use this equation, this transfer function, and give it some numbers. So let's just go to MATLAB right now, and then I will enter those into MATLAB. Right there. And then we have, oops. Okay. And so I am going to give some value to these coefficients and see where the roots of these things are. So it's taking us a lot of time. We have now the prompt. And then we say, okay, how about if I enter a transfer function in such a way that I have the numerator is equal to, I think it has the power of s, so I'm going to put a 1 or a 2 rather, 2 and a 0 here. All right. This one here has 3 terms. So I am going to enter a value there just for the sake of example in here. Okay, here we go. Denominator. I would say you have something like 2. Oh, 2 and then I didn't do it yet. 2 and then 10 and then 200 and then say return like that. And if I define the transfer function g is equal to the transfer function of the numerator and the denominator. And if I click here, there it is. See, so now what do I have? Do you see in there? This form is exactly the same as this. Yeah? Very good. If I look at where the roots are, I think we could predict how the system will respond. So why don't we look at a chart that shows us in generally the responses. We have in here a graph that shows where the where the roots are, the system has different response. So in here, for example, if it is a damp system, it will respond like this. Or if it is on the real axis, it will be overdamped and it will produce like this. But if you go to the other side, there is some bad news there. If it is over here, if it is just on the imaginary axis, there's two oscillations only. If you go farther down here and you have complex conjugates of this system, you see it on the right hand side, it grows, so it blows up. Okay. So let me just do the transfer function here so you can see the response of this. If I do where are those roots, I am going to get this kind of plot. I mean, sorry, this kind of, yeah, I think I'm gonna get them, yeah, right there. So you see in this case, you have one that is a 0, and then the other, but you see the green and the blue gets just up to that point and the green does too. So it never goes to the other side to be unstable. But this is the way we have calculated a test called root locus that actually gives a value of a gain and changes the coefficients to the point that you changes the the location of the roots, and therefore it's like this, and this one is stable.